So we will start with the work of of Oliver Newman from Institute of Technology, Germany, with the work in managing anomalies in energy time series from autonomous forecasting. Thank you. This is better.
Thank you for the introduction, and welcome you all to my presentation. I now want to talk about anomalies and energy forecast in energy forecasting actually. And because before I start, I just thought I will give you a short motivation why anomalies are interesting. We heard about before in a presentation about anomalies and why we should take care about them. But yeah, I just want to give another motivation for you all. First of all, I think we all agree that we have to face the energy transition challenge. So we should keep in mind that we somehow have to switch from fossil fuels to renewable energies. And that's what we actually do. We heard it in Brazil. The share of renewable energies increased over the time, and it will way more increase over in Europe, for example, as you can see here in the left figure, and also over the world. But renewable energies have one problem. They are much more volatile than fossil fuels because a normal power plant driven by fossil fuels, you can say in 6 hours I need, let's say, 50% more energy. Let's put them up. Yeah, it's no problem. But when we think about renewable energies, which is usually let's say solar or wind, you couldn't say we need 50% more in 6 hours. So that's a problem, and that we have to face. And one option for that is we can use energy forecasts. Because if we know which amount of energy is produced within the next, let's say, 6 hours, you can store energy and shift demand and something like that. But if you go further and think about energy forecasts, you also have to think about the models you want to train, because the literature says or shows that often current state-of-the-art models, as we see in our session and other presentations, I think, networks or models like neural networks are one of the state-of-the-art models to train. And also traditional models like random forest also need data. And when we think about data, we have to look at the data we have and the data quality. And we look at them, often the data quality is not that good when we have real-world data. For example, we saw that we have on the campus a lot of smart meters, and we also have smart meters at our campus. And we looked at them and saw that they have a lot of issues with the data quality. For example, missing data. And it depends on this smart meter, how they handle if a measurement doesn't record it correctly. Sometimes they just put it to 0 or something like that. And that leads us to the problem: if we have such anomalies in our data, how can we handle them, and how can we prove the forecasts so that it doesn't matter if we have anomalous data or not? And that is what I want to talk about today. Before I start showing you the anomaly strategies we evaluated in the paper, and that I want to show in the evaluation afterwards, I want to show you what our experimental setup is. We use the electricity load diagram dataset from UCI, which actually is a 4-year dataset from 370 different buildings, and you can just use them. And we assume that they is kind of anomaly free. As you can see here, for example, there are some weird data points, but we just assume it's kind of anomaly free. Because what we did, we had a previous paper where we presented or evaluated different kind of anomalies which are normal when you look at smart meters, for example. And we had 8 different kind of anomalies. For example, the row above is from technical faults, and the smart meters often record energy, not power. And for example, the first anomaly is if the energy time series drops to 0 and goes back to the actual value. That happens, for example, if the smart meter sends data to the record server and the package somehow gets lost and the server don't receive any energy data. And then he just says, okay, I don't receive any data, so the energy probably is 0. It's not true, but yeah, that's an anomaly. And what's happened then, if you derivate the time series to get the power, you get a negative peak, as you see here. When the energy time series drops to 0, then it's 0 because it doesn't change, and it goes back to the actual energy when the connection is established again, and you get such a positive spike. I don't want to go through all of these anomalies. You can read the paper if you are interested, but I just want to motivate that we don't just use anomalies we think are useful. We actually investigated the smart views and took anomalies which are common. And the unusual consumption are just patterns where the consumption pattern is significantly different from the days or usual consumption. For example, it's way lower than normal or way higher than normal. Then we implemented all the stuff based on our PyWatts workflow pipeline. It's a framework in Python where you can do graph-based workflows or implement graph-based workflows. And within that workflow, we used scikit-learn, PyTorch, and TensorFlow to implement the models. And we have a broad range of models which we use to train, for example, last day and last week as a baseline model, and also linear regression, random forest, support vector regression. Profile neural network is a neural network from our team where we add different kind of profiles into the input space of the neural network, and just simple neural network to compare the impact of the managing strategies. Now we come to the actual managing strategies. And the first strategy which we evaluated is just to do nothing. It's maybe a little bit uncommon, or you wouldn't want to expect that. But of course, one idea is just to say it doesn't matter. It won't impact the model so much. So just train it and the model learns by itself, which is useful and which is not. The second strategy is a detection strategy. There we use detection methods to detect anomalies and just pass the model an additional feature that says where the anomalies are, and the model by itself should somehow handle it. It's like an end-to-end learning approach. Yeah. And the last strategy is similar to the previous before. You detect the anomalies and you know where they are, and you don't let them handle by the model. You handle them by yourself with a way you think it's useful. For example, just do linear regression within the data points that are wrong. Yeah, and here you can see an example. The gray line is the actual time series. The green one is the anomalous time series. So you can see here an unusual consumption pattern. And we used the anomaly detection approach to detect the points, which are now crossed red, and compensated is, which is actually the result of the crossed result. Right. So now, if we go to the evaluation, we used, in the paper, there are different kind of detection methods explained us. We just used one detection method based on a neural network and compensated it by a linear regression. And that's the actual result. You can see here the dark green one on the left side is the raw-based detection one. Anomaly managing strategy. And the second one is the detection one, and the third one is a compensation. And the last one is just the anomaly-free case. So we don't have any anomalies in the data, actually. And as you can see, we have, in some cases, we can improve the performance of the model when we compensate the anomalies. But we never reach the actual performance when we don't add any anomalies in the data. And there's also a difference between the technical faults and the unusual consumption, because the unusual consumption is more often it's improving. The managing strategies improves the forecasting performance more in the unusual consumption data or anomalies. Yeah. So that leads me actually to my last slide, and I hope you can understand that, or I can show you to that compensation is the best anomaly managing strategy between the three, because so it's interesting to think about how to handle these anomalies. But as I also saw, or as you also saw, we are not at the level of anomaly-free data. So anomalies always reduce the performance of the models we evaluated. So compensating improves the forecasting accuracy depending on the anomaly type and model, but there more work done or needs to be done to improve the detection and the compensation of the anomalies. So what we can do to improve that further, we can evaluate additional anomaly types and determine their characteristics and improve by that the models to detect them. And also, as I said, we need to improve the anomaly detection algorithms to meet the actual anomaly-free use case, which would be nice. Yeah, and that's actually all of my presentation, and that's me. And if you have any question, let me know.
Thank you, Oliver. The audience want to do some question?
Thank you for your presentation. I was wondering if you can elaborate a bit on the compensation strategies that you've used.
As the compensation strategy, we only use the linear regression between the points, but there are, of course, several other options. For example, you can also use a neural network to train it. We have a paper wrote about copy-paste imputation, it's called. You look about the pattern without the anomalous part and try to find similar patterns within the data set you currently have. And if you find similar patterns and the time series you have match in that pattern, you can replace the anomalous space with the not anomalous time series space. And that's so like copy paste them into that part, for example. Yeah.
Okay, thank you for that. I have another question as well, which is, in your experience, how common are these sensor anomalies or data collection anomalies?
What do you mean by common?
Like how often do they occur?
Okay. They are actually quite often. We set the percentage up to 5 within the data set. The 5% of the data is anomalous. And we have a energy lab where we have several kind of energy smart devices. For example, solar PV planes and also smart meters. And as far as we recognize, they are often not that perfect, let's say like that. They often have problems with the data quality, mostly due to some software bugs. For example, we have smart meters that can record data to a database, and when they don't have the connection to them, then some stuff happens. And yeah, as I said, for example, they just write not 0 if the database don't collect any data in the missing space because the smart meter itself has no memory to store them. But that's not good. Yeah, maybe in a few years the data quality gets better when the data and when the hardware and the software improves. But currently, maybe also due to the fast change in the energy transition, as far we can tell with the hardware we have, that often data quality is a large problem. You can say, let's say, 5 to 10% of anomalous data. Yeah.
Okay, quite interesting. Thank you.
Thank you, Oliver. If you just can return some slides about the second method that you try to mimetize the detection. You pass the last the forecast method. You pass the kind of detection that the first algorithm take, and also the period of the detection. It's correct, this affirmation? Just elaborate, just to think better.
Do you mean if we
Yeah,
don't?
this second one, you pass
Yeah.
like the kind of detection, the if you are the saturation, some zero, and the period of detection to
Yeah.
the forecast algorithm.
In this, the model that in the first and second strategy are actually the same.
Okay.
It has the same input. In the second one, the model also gets the result of the detection. So it gets the time series and additional time series just with zeros and ones. So if it's anomaly or not.
Just
And
anomaly or not
yeah.
the kind of an anomaly.
Actually, that depends on the model we used for the detection method. That one we used in the evaluation only detects anomaly or not, because we used a conditional invertible neural network approach, which maps the time series into the latent space, and we just look if the point is far away from the latent space, so it's out of the normal distribution. And if that's the case, it's an anomaly. And because of the model structure, we can't tell what kind of anomaly it is. We just can tell it's an anomaly or not.
Okay.
But there are also models that pass the actual detected anomaly. We also had models implement that.
Nice. Thank you, Oliver. Some other question? Oh, please.
Thank you. Nice presentation. I was wondering about your because in my experience, when you experience these anomalies, they are not just like a single data point. They occur across I don't know, multiple minutes or hours. How did you kind of go around this?
Yeah, that's actually a large problem, and we think it's maybe also a problem why we are not that good in the improvement, because we have a detection quality of about 50 to 60%. So we detect 50 to 60% of the anomalous data, but we couldn't improve it so much, and that's probably because all of the unusual consumption and the first two of the technical false anomalies are time-based anomalies. So, for example, the network connection get lost for 1 hour. We also noticed in the data anomalies for multiple weeks. So, and that's really a problem how to handle that. And we don't evaluate approaches where we just leave out that data. We wanted to use all of the data for training. Copy-paste imputation, as I said, is one example, but all other compensation approaches are not that advanced. We don't reach the actual data often. And then using generic approaches, GANs, or also conditional invertible network would be an idea to maybe generate data, which is kind of useful. But if you use that data to actually do forecasts, the forecast also would probably not that good, because you don't have the actual historic time series.
Thank you.
Thank you again, Oliver. Nice
Yeah, thank you.
presentation.